Hello and welcome. In today's video, we will be going over topic 3.10, linear approximation and differentials. So to start out, we're going to be going over just some basic differentiation, just make sure we know how to find the slope. Then we're going to get on to the new stuff. So to start out, what is the, we must take the derivative of this function, and we will get dy dx is equal to sine of x times by the derivative of the inside, which is cosine of x, which is a cotangent, but I'm not going to write it as such. And then we just have to plug in pi over 2, and we'll see that this is going to be or pi over 2, not 0, and that's equal to 0. All right. For this next one, we have to take the derivative with respect to x. And for this time, instead of it being a chain rule, it is a product rule. So we get 2x times by e to the x plus x squared times by e to the x. All right, and now we have to evaluate this at x is equal to 1. So we get 2 times by 1 times by e to the power of 1 plus 1 times by e to the power of 1. Summing all of this up, we get 3e. So, what exactly is linerization? So what practically supposes is, as we get really close to a line at a certain point, it starts to look more and more linear. And we can use this fact to use the derivative to approximate values around a point. So I have a few important coordinates here marked out on the graph f of x. I suppose I didn't mark the graph as f of x. So if we want to approximate a point, let's say we want to approximate, and I'll do this in just a small bit different color here, this point B. Well, how do we do that? Well, we know the slope at this point, and we know what the point is. So we are going to develop a line using point-slope theorem. So we know y minus the function at the point f of a is equal to f prime of a, because that's the slope of the line, times by x minus a. Now we need to solve for y, so we can just get this in function notation. So y is equal to f prime of a times by x minus a plus f of a. This right here is called the linerization of the function at point A. So now if we want to evaluate this at point B, all we have to do is plug in b to our linearization here, and we still have this f prime of a. This becomes b minus a plus f of a. And then we can just evaluate it. And that will give us our approximation of the function. So now I've got some practice problems here with linearization. I'll walk us through them all. So for this first one, we want to start out by asking ourselves, what function does this look like? And it looks to me like x to the power of 4. So we are going to say our y is equal to x to the power of 4. So then we're going to take the derivative of this so we can find its slope. Alright, so we have dy dx is equal to 4 times by x cubed. That's good and handy now, but what do we do now? Well, we want to find a point that evaluates easily near this point. And I think the point that we want to do is 2. So we're going to say x is equal to 2. Or rather, a is equal to 2, but that's... I digress. So we're going to take dy dx and evaluate this at a is equal to 2. And as you'll see, we will get 2 to the power of 3 is 8, times by 4 is 32. So that's our slope of the line at that point. But now we need to also find the coordinates of the function at said point. So we know that we need a point. We know the point has coordinate 2, but what's the second point going to be? Well, we have the original function right here. What's 2 to the power of the 4th? 2, 4, 8, 16. Alright. So now we have all the information we need to find the linearization of x. So we know the linearization of x is equal to the slope, which is 32, times by x minus the point that we chose, or the a, plus 16. Now, all we have to do is plug in our value b is going to be alright, so our b is 1.999. So now we get the linearization of 1.9999 is equal to 32 times by negative 0.001 plus 16. So finally we get this answer of like negative 0.32 plus 16, which is going to give us a answer of 15.968, if I did my math right. That looks right. Alright. So now, for this next function, this looks like 1 over x. So we're going to say y is equal to 1 over x. We know our a value is going to be 4 because that's what's going to evaluate easily. And then finally, our b value is going to be 4.002. Alright. So, to start out, we take the derivative, and I'm going to rewrite this as x to the power of negative 1 of both sides with respect to x. So, we get dy dx is equal to negative x to the power of negative 2 for our answer. So now if I evaluate this at a is equal to 4, or when x is equal to 4 rather, but I'm going to keep calling it a, we are going to get negative 1 over 16. So we're going to get negative 1/16. Alright. Now, we just need to plug in our 4. So, y is equal to 1 over x evaluated at a is equal to 4. So we just get 1/4. So we can now write down our linearization of x is going to be negative 1/16 times by 4, or sorry, not 4, x minus 4 times by, or sorry, not times by, plus 1/4. Alright, so we get the linearization of x is negative 1/16 times by, or sorry, around 4.002. It's going to be 4.002 minus 4 plus 1/4. Linearization of 4.002 is going to be equal to negative 1/16 times by 0.002 plus 1/4. And then now I'm going to just plug this into my calculator here to get a final answer of 0.250. And you may be asking yourself, what are these actual values so far? And I will give you those. So I'm going to write them actually out in orange here. So for this first one, it's going to be 15.968. Look at how close those two approximations are to each other. Of course, there's a bit more decimals in this one, but that is still a very close approximation. For the second one here, we get 0.250. Again, a very close approximation here. Alright, and now time for this next one. So, normally we don't like working with degrees, but I'm going to bear with myself here for just a moment and say that this is approximately going to be the same thing as cosine of pi over 6. So we're going to take the derivative of this cosine function instead of this one, because if we take the derivative of this one, then everything breaks. Simple enough. Alright. So, the derivative with respect to x of cosine of x, well, we should already know this to be negative sine of x. Cosine of pi over 6 is going to be equal to square root of 3 over 2. Negative sine of x evaluated at x is equal to pi over 6, because pi over 6 is 30 degrees, if you did not know that. That is going to be negative 1/2. So now we have the slope and a point. So now we can make our linearization. So linearization of x is equal to negative 1/2 x. So we get x minus, x minus the value a, which is going to be 30 degrees, plus the square root of 3 over 2. Now that I have all of this information, we can find the linearization of x is negative 1/2 times by -1 degree, which we're just going to call -1, or actually I suppose I should probably put this in radians. Okay, time for the mess that this is. -1 degrees times by 180 degrees for 1 pi. So now we're going to sub this in. So we just get -pi over 1/800. And then plus the square root of 3 over 2. So finally we get the linearization of x is going to be -1/2. Or actually, I'm just going to plug this into a calculator since this has pi's in it. And for our final answer, we get 0.874. If I plug this into my calculator in degree mode, we will see that the value that the cosine of 29 degrees is 0.875. And that's actually the same as this. That's just I forgot to round. I truncated instead of rounding. All right. Now on to the topic of differentials. So, what is a differential? That is a wonderful question. Okay, to start out explaining this, let's say that we have a function y is equal to f of x. Well, we're going to take the derivative of this, as we want to use this for an approximation. So we get dy dx is equal to f of x, f prime of x. So, now what if I want to get a specific change in our y value corresponding to a change in our x value? Okay. So, let's say that I have a function y is equal to x squared here, and I want to know how much this changes from, let's say, 0.5 to 1. How much is our y value changing from 0.5 to 1? Well, our derivative over here actually gives us a way to do this. So we're going to treat this dy dx like a fraction here and multiply it over to the other side. So we get the dy, the differential of y, or the differential dy, is equal to f prime of x times by dx. How is this useful for us to approximate something? Well, if we are given a certain value of x and a certain value change in x, we can use this to approximate the change in dy. However, we can also, if we are given a value x and a certain value change in y, we can also figure out how much of a dx we need for that value to occur. So, going back up here to this y squared example, let's work it out. So we have y is equal, so y is equal to x squared. So then our dy dx is 2x. Now we want to get the differential y by itself, so we get 2x times by dx. We know that we want to evaluate this at the point x is equal to 0.5, and change in x is also equal to 0.5. So we get 2 times by 1/2 times by 1/2. So our differential dy is going to be increasing, assuming the same slope, by 1/2. So that's just an estimate of how much y is going to grow. Finally, if we want to know the relative error of our approximation, what we can do is we can take the change in v, or really in this case it's going to be the change in y, and divide it by y. So we are going to really get the differential of y divided by y, which in our case was 2x dx divided by x squared. Plugging in our values, we can find the error, or the relative error, which we can cancel one x and the x squared, so we get 2 times by 1/2 over 0.5. So what this is going to give us is 2. So our relative error here is 200%, which is, 200%, because you have to multiply that by 2. Very much of a very big error, but it gets better with smaller and smaller dx's, but also bigger numbers. Alright. For the purposes of time, we're only going to be doing this first equation, so we want to find the change in y for the given values of change in x and dx. So you won't have to find the error for this one. So we're going to take the derivative of this, so we get dy dx is equal to 2x minus 4. Now we want to multiply the dx over to the other side, so we get dy is equal to 2x minus 4 times by dx. Plugging in 3 and 0.5 now, we can get a dy is equal to 2 times by 3 minus 4 times by 1/2. So we get the dy is equal to 6 minus 4 times by 1/2. This evaluates to 2, so we get dy is just equal to 1 for our given value of x and change in x. Well, that's all I have for you today. I hope you have enjoyed, and I hope that this has made differentials and linearization a bit easier for you. I hope you'll have a wonderful rest of your day. Goodbye.